go ahead.
Yeah, thank you for having me here. First time in Zurich. It's really nice. This is joint work with Calvin Smith, my student in Wisconsin, and my colleague Justin Su, who recently joined us. So let's start at the very beginning. First, there was Turing. And in 1949, Turing wrote probably the first proof of a computer program. So he was a forward-looking guy. He was like, look, we're going to be writing programs. These programs may not be correct. We need to prove them correct. And in this 1949 paper, just a few pages, he essentially writes out something that looks like a Hoare-style proof, way ahead of Tony Hoare. Yeah. Then, in the 70s and 60s, we developed Hoare logic and things like that. So essentially formalizing Turing's informal ideas. Then in the 80s and 90s, we came up with model checking and abstract interpretation. And then, in the 2000s, this culminated in industrial tools that you can actually push a button and it does these proofs automatically for you. But most of these proofs, more or less, are proving something of the form assert x is not equal to null. So they're reachability properties. A bad state where x is equal to null should not be reached. But as software becomes crazier and crazier, it does all sorts of things. This is, doesn't cut it. Okay, so we're moving towards a new world where software is doing really complex things that affect us as people and as a society. And there are many questions that we need to answer. So we've been looking at questions like, is my data private? Like if a piece of code is looking at my data, is my data private, and what does that mean? Okay? If a piece of code is, learning from data and making decisions and that affect my life, is that piece of code fair in some definition of fairness? So these are the kind of questions we've been thinking about, and today, in the interest of time, I'm going to focus on question number one. Okay? Is my data private? It goes through an algorithm does some statistics. Is it leaking my private information? So it turns out that making sure your data is private is a tricky problem. Okay? So you can't just de-anonymize your data. So the simplest thing to do is just to remove names, for instance, dates of birth, social security numbers, these unique identifiers. But in many studies, people have figured out how to reverse engineer that and de-anonymize the data on large data sets. Okay? So the field of differential privacy came in and said, let's fix things up. And the general idea of differential privacy is to prove that a specific piece of information, like your own information in a data set, is not contributing too much to the output of the algorithm. Okay? So essentially, if you remove your data or you put it back in, the output is more or less the same. Okay? So imagine that we have a hospital, and there are three kinds of ailments or diseases that people go to the hospital for. Okay, so A, B, and C. And we asking the question, what is the most prevalent disease in this hospital, right? So in this case, maybe we'll say A because it's the first disease and has the largest number. It's tied with B, but let's say we say A because it's the first one. Okay? And now, a new person joins the hospital, and so he has disease B, so a new patient. Now we run the algorithm again, and it will say B. Okay? So that person's information completely changed the output of the algorithm, and as a result, we could infer that that person came in with disease B. Okay? So differential privacy says this is too much. In order to avoid leaking that person's disease, we want to add noise to this program P that is performing the calculation. Okay? So this program P becomes now a randomized algorithm. So essentially, semantically speaking, program P is outputting a distribution. Okay? Can everyone see this? It looks a bit blurry. Yeah? Okay. So you can think of it as outputting a distribution, but the data analyst only sees a single sample when they run this algorithm. But semantically speaking, from a programming language's perspective, it's a distribution, and then you run the algorithm again, it gives you a different distribution. Okay. So when these two distributions are really close to each other, then there's more privacy. When these distributions are really far apart, then there's less privacy. So that's sort of the definition of privacy that differential privacy talks about. And this, seemingly theoretical idea has moved from theory to practice, and we're seeing it in many different places. So for instance, if you're using Google Chrome or Apple iOS, your browser or your phone is sending information constantly to Apple or Google, and that information is being sent in a private way by adding noise to it. Okay? So Uber internally claims to be using differential privacy. So if data scientists at Uber are analyzing the vast swaths of information they're collecting from their cars, and they're interfacing through the data through this noisy channel of differential privacy. In the US, the Census Bureau, which does the, a large census of the population every 10 years or so, is employing differential privacy in the 2020 census, and they're hiring tons of computer scientists and statisticians to implement that, and the code is open source. So it's really exciting. So this notion of differential privacy can also apply to decision making, not only data analyses. So imagine that these two inputs are two people that are similar. So just like two databases or two sets of queries that are similar, two people that are similar, and these programs are making decisions like whether to hire them or whether to give them a loan. And you could think of these distributions as the probability of giving them a loan and probability of hiring them. Yeah? So now this notion of differential privacy can enforce that for similar people, the outputs should be similar, okay? And therefore fair to those individuals. So no one can say, look, my friend who has the same resume didn't get this job, but I got it. Okay. So when people develop these algorithms, what they usually do is they say, look, I have a standard data analysis, like say a program that computes the sum, or maybe something sophisticated like stochastic gradient descent. And this stuff is not private, okay? So it does not have any privacy guarantees, and I want to make it private. So theoreticians, usually theoretical computer scientists, develop an algorithm. Okay? Then they write two theorems, one that says that the algorithm is indeed differentially private, and one that says that the algorithm is accurate. And what we'd like to do is to construct an automated verifier that takes an algorithm and takes these two theorems and spits out a proof. Okay? So far, these proofs are done by hand. And then they're published at Stock and Fox and other venues like that. So the first theorem that is more interesting, I would say, is the differential privacy theorem. Roughly speaking, okay, I'm saying here roughly, it says that take two databases that are similar to each other, run the program P on the first database. What is the probability of it returning an A, some A, for any A you want? This should be very close, or less than or equal to, sum multiplied, constant, multiplied by the probability of running it on the second database and getting the same answer. Okay. So when this constant is 1, we're really saying that these two probabilities are the same, okay? Which is, gives you nothing. So you can satisfy this pretty trivially by just returning 42 all the time. Okay? You don't want to do it. So it's really easy to get a private algorithm. You just return a constant all the time. No information is leaked. Okay? But of course that doesn't work. So we really want an algorithm that is pretty accurate yet pretty private at the same time. So at the same time we want to prove an accuracy property that, roughly speaking, looks like this. You run the private version of the algorithm, you run an exact non-private version of the algorithm, and you want to prove that they are, theta apart. Okay? And because this algorithm is randomized, there's always a probability of failure, meaning the probability that, the difference between the real answer and the answer you're returning is really large, okay? Beyond this theta. Okay? So these are the two properties that we're interested in. So why do we want to automate this verification process? So the short-term vision is that these theoreticians don't have to write these proofs manually, and they can iterate really quickly amongst many different algorithms. Okay? So we can aid them with these automated tools. Now, once we have a verifier that can prove things about these algorithms, then we can implement a synthesizer that can discover algorithms and prove them correct simultaneously. And in that world, we can put theorists out of work. There will be no Stock and Fox, and they can all go back to proving P equals NP and more interesting problems than designing privacy-preserving algorithms. So this is long-term vision, so it's a really hard problem. And I'll tell you why it's hard. It's because these algorithms, proofs are actually ridiculous. Okay? So this is a very simple algorithm. All it does is it computes the maximum element in an array. Okay? That's it. Okay? This is the proof of its privacy from the Dwork and Roth book. Okay? So this is an informal proof of privacy. This is another proof of privacy of another very similar algorithm called the exponential mechanism. Okay? So for someone who's from outside this field, like myself, coming in, I look at this stuff, it's pretty scary, It takes me like an hour just to kind of understand every step in this algorithm. And for this one, it took me really a long time. I had to go and watch YouTube videos, lectures by, famous theoreticians, kind of, walking step by step with this algorithm and showing examples of why it works and what it's doing and so on, for me to really appreciate what's going on. Okay? So it's a tough algorithm. So we decided we were going to automate these things. Just automate these proofs. And since we're working with a randomized algorithm, I mean, these are randomized algorithms, right? We looked at the literature for, probabilistic systems, randomized algorithms, and so on, and how can we automate such proofs? So the literature is vast. There's so much work on probabilistic systems, probabilistic logics, and so on. So there's a lot of logics, okay? So these are mostly, you take Hoare logic and you throw in probability. And just as with Hoare logic, it's really unclear how to actually, automate Hoare logic. There's so many ways of doing it. Okay? So these are generally not automated. There's work on martingales and pre-expectation calculus, which roughly speaking are like invariant generation and weakest preconditions. But then again, once you get an invariant, what do you do with it? Once you get a weakest precondition in this world, you get a complex integral. And then how do you discharge that integral? So it's really unclear how you can prove the theorems I showed you in the previous slide. And then there's the whole world of probabilistic model checking, but usually they're interested in finite state machines, okay? Finite state systems, and they can't work with the symbolic distributions that we're working with. Okay? So today I'm going to show you two techniques. The first one is for proving accuracy properties, and I'm starting with accuracy even though it's a simpler problem and perhaps less interesting because the proof techniques are relatively similar. Okay? The intuition is similar. So then I'll switch to privacy. Okay? And I just wanted to also mention that we've extended these techniques to the synthesis world, so we can actually synthesize and discover some of these algorithms automatically. Okay? So the underlying theme across all of these works is that we can get rid of probability and just use logic. Okay? Use SMT solvers and the tools that we all know and love from the standard automated verification toolbox. Okay? So I grew up scared of continuous mathematics. So whenever I see probability, I say, how can I get rid of probability? Okay? So that's my gut reaction always. And in this case, my gut reaction worked. So let's look at a program, and this slide is really important because I'm going to come back to this program a bunch of times throughout the talk. So this program takes a set of queries, okay, Q, so this is a list of queries, but think of each query as just returning a number. Okay? So now you can think of this Q as just an array of numbers. Okay? And what this is doing is returning the index of the largest query. So this is just a loop that returns the maximum index in an array that you will see in CS 101. Okay? So this is the index that it returns. Okay? So if you get a bunch of queries, you run them, this returns the maximum answer. You say query number 4, return the maximum answer. Okay? The only catch is that this line over here. So instead of looking at a query, QI, we're looking at a noisy version of it. Okay? And this noisy version is sampled from the Laplace distribution. Okay? So essentially we're sampling from a Laplace distribution that is centered at QI, and 2 over epsilon is a parameter that indicates how fat this distribution is. Okay? So when we roughly run this algorithm once, we're looking at a noisy version of this. So we're looking at a more ballpark version of it. So maybe we'll return Q2 instead of Q4. Okay? So we may be returning the wrong answer. So we want to prove that this algorithm is both differentially private and accurate. But first, let's talk about accuracy. Okay? So I'm going to go back all the way to the beginning to how to prove correctness of a standard program, and then, meaning it doesn't have any probability, and then extend it with probabilistic sampling statements, and then we'll go back and see how a proof of this program can be automatically generated. So I'm going to view programs as control flow graphs or paths through a control flow graph. So this is just a simple program, a single path with a single statement. So the program increments, sets y is equal to x plus 1. There's a precondition x is greater than 0, and a postcondition y is greater than 0. And if these are mathematical integers, then this pre and postcondition are correct in Hoare-style reasoning. So how do we prove this correct? Simply speaking, we just change the font turn these, sans serif into serif, and then give it to an SMT solver, and things work out. So x is greater than 0 becomes x greater than 0. This becomes y equals x plus 1. This becomes y is greater than 0. And then we put in Boolean connectives between them, and we ask the SMT solver, is this formula valid? Okay. And in this case, the SMT solver says yes, the formula is valid, and as a result, I know that my program is correct with respect to this pre and post condition. All good? All right. Cool. So now if we have a more complex program, perhaps with loops, then simply speaking, we can look at every possible execution through the loop, like 1 iteration through the loop, prove it correct, 2 iterations through the loop, prove it correct, 3 iterations through the loop, prove it correct, and so on and so forth. Of course, there could be infinitely many iterations of the loop. Then we use something like an inductive invariant to prove that no matter what happens in any number of iterations, the proof will still go through. So I'm not going to talk about inductive invariants. I'm just going to push them aside. Okay. So now let's imagine that our program has a sampling statement in it, like this. Okay. So here we're flipping a coin, and we're getting true with probability p, or heads, okay, and false with probability 1 minus p. Okay. So of course, the p and 1 minus p may be in the opposite heights, but this is just an example. So as a precondition, I'm going to say that this p is between 0 and 1. And what I would like to prove is that x is equal to true at the end of this execution, except with a probability of at most 1 minus p. Okay? So this is my probability of failing to satisfy this post condition. Okay? So my logic, or my assertion language, gives me a Boolean condition and a probability of failing to satisfy this Boolean condition. Okay? So does everyone agree that this pre and post condition are correct? It's pretty easy to see because the probability of not getting true is 1 minus p. Okay, so it's very syntactic here, the proof. But the challenge is, if I want to automate such things, how do I do it? And specifically, I want to do it with an SMT solver. Okay? I want to just not care about probabilistic reasoning. Okay, we've spent a lot of time of people's lives building these solvers. Can we use them in this setting? So here's a trick that we can do. We can rewrite this program into one that does not have any probability, okay, as follows. So this precondition is the same, but we're adding a new variable called w that is initially 0. And w is going to be a ghost variable that maintains the probability of failure of any execution. So now we will translate this statement into 2 statements. The first one says, I'm going to assume that x is equal to true. Okay? So this is really weird, because as far as this sampling statement is concerned, x could be true, x could be false. Okay? And here I'm doing an under approximation, right? And if you put the traditional verification hat on, if you're proving something, you need to over approximate. You can't just throw away possible executions. But here I have thrown away. Specifically, I've thrown away the case where x is equal to false. Okay? So I've thrown away the case where x is equal to false. I've forced x to be true. And in addition, I've paid a price for it. And the price was 1 minus p. So 1 minus p is the probability that x is equal to false, which is the execution that I've thrown away. So I can pay a price for it and put it in this variable w. And now I can prove the post condition that at the end x is equal to true, but there's a probability of failure that is at most 1 minus p. Okay? All good? So if I prove this program that does not have any probability, if I can prove it correct, then I immediately imply that this program up there, the probabilistic one, is actually correct. Yes?
So how do you know which of the executions to throw away?
That's the next slide. So in this case, I've picked a specific assumption about the value of x. But I could have picked many other assumptions. So we call them axiomatizations of the distribution. Okay? So alternatively, I could have picked x is equal to f. Okay? Meaning I could have assumed that x is equal to false, and I would have paid a price of p, which is the probability of x being true. Okay? But this would not have satisfied the post condition, because the post condition tells me that x must be true at the end. Okay? But here, I've assumed that x is equal to false. Bad assumption. Alternatively, I could have assumed that x is anything. So just x is assumed true. Okay? In this case, I'm essentially saying x is non-deterministic. Can be true, can be false, I don't know. And I would have had to pay 0 for this assumption, because this assumption captures every possible execution. And again, I would have failed, because I have to prove that x is equal to true at the end. So many different possible axiomatizations, even for just a flipping coins statement. So imagine now if you have a continuous distribution, what do you do? So the general form of the problem is I have a sampling statement of the form x is taken from some distribution. Maybe this distribution looks like this. Okay? Maybe it's continuous, maybe it's infinite and so on. Okay? But the general idea is that I want to assume that the variable x takes a subset of the possible values. Okay? Maybe these 3 values or more. Okay? And then I pay a probability of failure, which is the area under the rest of the curve. So everything that I did not pick, I measure the area under that curve, and then I pay a price for it. So that's the general view. So now, with that view in mind, what I'm really saying is that I have a sampling statement. I can assume something about it. It's a predicate of x. And then I pay a price, which is the probability that this predicate is not true. So what we have now is a program that does not have any probabilities in it, but this program has an unknown predicate that I need to discover. So what does this look like? Program synthesis problem. It's a program with a hole. So now I can take this thing and I can encode it as a there exists for all formula. So there exists some predicate r over x, and then for all w prime, meaning the initial value of w prime, and the variable x in the program, this encoding of the program, which is over here, implies the post condition, which is that x is true and w prime is less than or equal to 1 minus p. You don't have to read this, really, but this is all this is doing is encoding the verification condition for this program. But the important part is that there's a piece of the program that's missing, and I need to discover that piece of the program, which is the predicate r. Right? So now, if I have a program that has multiple execution paths, I can prove that this path satisfies the post condition except with a failure probability of P1. This one satisfies the post condition except with failure probability P2. This one with failure probability P3. And then I can sum all that up using the union bound, and then I can say the whole thing fails with probability sum of all these minor probabilities. Yes?
On the previous slide, you need to assume that you know how to compute that probability.
Yeah, so we ensure that this statement has a closed form that we can encode in the semantics of this. And I'll show you an example of a complex one. Yeah. Right. So, but if you have many execution paths, you can just sum up the failure probabilities and get a failure probability for the full program. This sum can, of course, go to infinity, but there are ways to take maxes instead of sums. I'm not going to go through those specific cases. Okay, you can look at the Popple paper. So now let's look at a more complex distribution. This is the Laplace distribution that we saw earlier. So this is we're sampling y from Laplace. The mean of the distribution is x, and the scale is s, okay, meaning how fat this distribution is. And we can assume, okay, we can create a system of axioms or a family of potential axioms that say that x is in this region. The sample we get is in this region, okay, in this pink region, and the failure probability is the white area over here. And I can pick any possible interval of any size. So it turns out that this has a nice form. Okay? It just says that the distance between x and y, the mean of the distribution, and the sample I'm receiving, is less than or equal to this quantity. And this quantity has a parameter in it, which is a function over program variables. Okay? So whatever you pick here, plug it in, you get a different axiom. Okay? come up with any function that is between 0 and 1, you'll get a different axiom. And this function happens to be the area under the rest of the curve, which is the failure probability. Okay. So now if I pick something really large over here, then this whole thing goes close to 0, meaning that this interval shrinks really around x. So I'm making a very, very strong assumption, but I'm paying a very large failure probability because my assumption is really tight. Okay? So you make a tight assumption, you pay a lot of money. Okay? You make a weak assumption, you pay very little. Okay? So that's the give and take here. All good? All right. I like people who nod their heads, so keep on nodding. All right. So let's go back to our program. Right? If you look at the book, what it says is that we want to prove something about this program, and specifically what you really want to prove is that this is returning the index of the largest element. Then this element that you're returning should be pretty close to the largest element. Okay? Maybe not larger than all elements in the array, but pretty close to the largest one. So the proof specifically has the following precondition, that P, or the theorem statement really, not the proof. We have a failure probability P between 0 and 1. Okay? So notice that P does not show up in the program. This is just an artifact of the theorem. Okay? And then the postcondition that I want to prove is that the query that I'm returning, its index, okay, so Q of R, is greater than or equal all other queries, okay, which is exactly what I want, but there is some slack, okay, minus some amount. Okay? Because it's a noisy program, I can't ensure that it's always returning the largest amount. There is some slack, and you don't have to understand this. All you have to know that this expression is parameterized by P, by the failure probability. Okay? So if I pick a large failure probability, this whole thing becomes really small, and then I can make a pretty strong statement about this, about how good the return answer I have. But I have a large probability of failing to satisfy that. If I make P small, then I can't. This slack variable, slack expression increases, and I can make pretty rough estimates. Okay? And this whole Boolean postcondition can fail with a probability of at most P. Okay? Yes. This is a theorem statement, written by someone who understands this program. Yeah. So you could imagine inferring such things automatically. Right now, our technique takes a theorem and proves it correct. So how does this theorem? How do you come up with this? Is up to you, up to the specifier. Okay. Yes.
So I don't understand the significance of P yet. So you're just saying that P is some real value from 0 to 1?
That's right, yeah.
No one's fixing it anywhere?
Yeah, so this is just a parameter of the proof. Okay? And whenever you look at randomized algorithms, you usually have a proof of this form. So your theorem is parametric in the sense like pick a probability of failing, this is what you can assume.
Okay, so that means P is universally quantified here?
Correct. Okay. P is universally quantified, yeah. Cool. So if you showed me such a theorem in a program 2 years ago, and you told me, can we prove this thing automatically, I would have just laughed hysterically. But it turns out that we can actually do this, even though it has everything that is hard about automated verification in one slide. It has probability, it has loops, it has infinite state, it has universal quantifiers, it has arrays, and it has non-linear arithmetic, and it has transcendentals. It's nuts. Everything that's hard in a single program in a single slide. But it turns out that we can actually prove this correct automatically. And the key idea of the proof is to discover an axiomatization of this statement that shows up over here. And every time we encounter this statement, we assume that the answer that we're seeing, which is D, is different from the actual query that we're looking at. And the distance is this quantity. And the key part of this quantity is this parameter that we discover, which is the failure probability is P divided by the length of the array. So when you have a failure parameter of P divided by the length of the array, and the loop runs length of the array times, then the total failure probability becomes P at the very end. Okay? Because you are paying this quantity, this amount, every time you execute the loop. You pay it the size of Q times, so then you'll pay P at the very end of any execution. Okay? So you get this failure probability P over here. And of course, there is an inductive invariant that has to be discovered. The inductive invariant looks, roughly speaking, like the postcondition, but you have to do some triangle inequality to imply the postcondition. But I'm not going to show you that. It's too much universal quantifiers. Yes. It could be. It could be in principle. Our proof system allows that. Our implementation is syntactic in the sense for any program statement, it always uses the same failure probability. In the proofs of privacy that I will talk about next, I will be, the crux of the proof is that you need essentially a scheduler that say, if the state of the program is blah, then I'm going to use this axiom. Otherwise, I'm going to use that axiom, and so on. So it gets really hairy really quickly. Yeah. In this case, we don't, but you could. Yeah.
I don't know if you'll talk about this, but I guess you can keep this log uninterpreted. Is that true?
That is precisely what we do. So the log is uninterpreted, and we just need to carry around the constant that is multiplied by the log, or whatever expression. Okay? So there's a lot of effort under the hood to deal with these things, but essentially the crux of it is it's all uninterpreted with some axioms about multiplication and division and so on. Yes?
I guess this approach is independent of the distribution that we have, or it doesn't depend on the Laplace distribution.
In this case, as I showed before, we have a parametrized family of axioms where all the axioms say that the value you have is some interval around the mean, right? But you could imagine crazy programs where you need to have an interval or a set of intervals and so on, and then you'll need a richer axiom family. So it is independent. It is dependent in the way that you have to define a set of axioms. Even though that set of axioms is infinite, it is limited. Okay? Other questions? Cool. Okay. So this was the accuracy story, and I'm going to move to the privacy story. And again, the theme is we're going to get rid of probability, and we're going to use logic. So once again, the story of differential privacy is that you're executing two copies of the program on two neighboring databases. Usually you remove or add one element, and you want these two distributions to be close to each other. If they're far apart, then you have less privacy. Formally speaking, this is written like this: for all neighboring databases, for all outputs A, and for any parameter epsilon, the probability of getting A if you execute the first program on the first database is less than or equal to e to the epsilon multiplied by the probability of getting A on the second database. And the key part of this statement is this constant parameter over here. As epsilon increases, then the two distributions go far apart from each other. As epsilon comes really close to 0, then this whole thing becomes 1, and then their programs are the same. Essentially, you're not leaking any information whatsoever. Okay, you're returning the same answer every time, which is not really useful. Okay. So how do we prove such properties? Okay, this is obviously a hyperproperty because we're looking at two copies of the program. So these proofs are tricky, and people have gotten them wrong in the literature. So there's a nice paper from Liu et al. At VLDB 2016, where they show 6 different versions of the same algorithm, and 4 of them were incorrect. Okay? Either the algorithm is incorrect, the proof is incorrect, or something's incorrect about them. And there are existing techniques for proving differential privacy, but they usually perform a very, very rough analysis. Okay? Yeah?
There's also a privacy budget associated with the query, right?
Correct.
I didn't see the privacy budget in any of this.
Yeah, so the privacy budget is whenever you usually execute a query or an analysis, and then a user of a database has a privacy budget, and it gets decreased. Okay, so here I'm looking at a single query or a single algorithm, independent of how the budget is maintained by a database maintainer. Yeah. So these techniques are very simple and conservative, and they get very weak bounds on privacy. And we want to automatically prove them. So the key idea comes from the theory of randomized algorithms. There's a technique called coupling proofs. Okay, so if you open a book on randomized algorithms, there's something called the coupling proof. And my colleague Justin Su and his collaborators, Gilles Barth, Marco Gabbardi, and others, they've shown how these things can be applied to the proof of differential privacy. But essentially, they're techniques where Hoare logics. And just as with Hoare logic, how do you automate it? The same question arises here. It's even a harder question now, because the logic is much, much richer. So the parameter space and the search space is insane. So our contribution is to think of those proofs as if they're games. And I'll show you why they're games. And once you think of something as a game, winning a game becomes finding a strategy to win the game. And a strategy is a program. Okay? Just as with playing chess, the strategy would be look at the current state. If the bishop is here, then do that. If I don't know what is there, then play that. Okay? So now we want to win a game, and games are inherently program synthesis problems. So you want to discover a strategy to win the game, such that whatever the state is, you satisfy some winning condition, winning criterion. Okay? And once you have that mindset of these proofs are games, then you can think of it as just a program synthesis problem. So what are these crazy couplings? I'll show you examples. So you have here two distributions, two Laplace distributions. One is centered at 0, one is centered at 1, but they have the same scale. Okay? So we came up with a notion of coupling called variable approximate coupling that makes our proof system work, but the details are not important. So a coupling for these two distributions is a ternary relation that says the following. I'm going to assume that they both return the same answer, C, whatever C is, and I'm going to record on the side the difference between these two answers, the difference in probability. Okay? Specifically, let's assume that they both return 0. The difference in probability is this distance between the red line and the blue line at 0. Okay? Specifically, this distance is e to the y. Okay? So it's the log of that multiplicative factor between the two. Okay? So this looks very much like the definition of differential privacy. This is the probability of getting C in the first distribution, probability of getting C in the second distribution. Okay. Now, if we have slightly different distributions, like this is shifted to the right, so it's centered at 2, then another coupling says, if you pick the same answer, then the distance between them is 2y. Okay. Now, the trouble is, even for two distributions, there are so many possible couplings, infinitely many possible ways of coupling the two distributions. Okay. So here's another coupling. This says, if you pick C in the first one and C plus 1 in the second program, then the difference between them is 0. Okay. Because if I pick C here, meaning 0, and 1 here, the difference between these two probabilities is 0 because they're the same probability. Okay. So I could have coupled them in so many different ways. Okay. And the trick of the proof is discovering the right coupling at the right time, just as with the proofs of accuracy, we needed to discover the right axiom for the Laplace distribution to get the proof to go through. So the general proof rule for this is that a program P is differentially private if, take any two databases DD prime, take any epsilon parameter of the program, there exists a coupling such that this is a coupling of the two output distributions. Remember, when you execute P on some database, it's giving you a distribution. And I'm saying that there exists a coupling C that couples these two distributions when you run the program on the two different databases. And this coupling is of the form that any two outputs have at most y between them in terms of probability distance, and y is at most bounded by epsilon, and therefore you prove epsilon differential privacy. Okay. So the trick is that these two distributions could be pretty complex, multivariate, so on, but our couplings, mostly work for Laplace-like distributions, very simple distribution, single variable. Okay? And the idea is that it turns out that we can compose such couplings and get a complex proof. So I'm going to show how this works on a very, very simple program, and then just briefly describe how it works for a more general setting, and specifically the report noisy max example. So this is the simplest possible program that is differentially private that you can write. It takes a single integer, maybe a count or something like that, and it adds noise to it. Okay? Adds Laplacian noise with a scale of 1 over epsilon. Okay? And returns y1. So it takes x1, returns y1, a noisy version of x1. Okay? And what I want to prove is that if I have another variable, x2, that is 1 apart from x1, okay? And I execute this whole thing, the second program, then the two distributions are, satisfy differential privacy. So if you execute the first program, you'll get some distribution. Let's say it's the red distribution. You execute the second program, you'll get the blue distribution, and they're 1 apart. Because I enforced by the precondition that they're 1 apart. Okay. So this is the picture we had on the previous slide. This is one possible coupling of this picture, of these two distributions. If we get the same answer in both distributions, the distance between them is going to be epsilon. Okay? So the trick is, how can I discover such a coupling that implies differential privacy? And it's going to be the very similar idea as before, as the accuracy case. We're going to turn these two programs that are both randomized into a single program that is non-randomized. Okay? Specifically, I'm going to say, okay, here's my precondition. I'm going to use a ghost variable, w. But instead of w capturing the failure probability, it's going to capture the distance between the two distributions. Okay? So y1 and y2 can get any value c. Okay? So they're forced to get the same answer c, whatever c is. So c is symbolic, so it's non-deterministic. And that's the cute part of the proof, is that these two stochastic processes are completely independent. Okay? So they both think they're independent and fun and great and cool, but then I forced them to act the same way. Okay? I forced them both to get the same answer. And then with this variable w, I just insert the distance between these two distributions, between getting c in the first answer in the first program and c in the second program. And then I just show at the end that they both return the same answer and the distance is less than or equal to epsilon. Now, as Alex suggested before, how did I pick this specific coupling? Again, there's an infinite space of possible couplings. Second, if these two appeared in a loop, do I always pick the same coupling? It turns out that's usually the wrong answer. You have to pick the right coupling in the right place. So proofs, roughly speaking, look like this. If some condition is true, then use this coupling. Otherwise, use that coupling. And this condition looks at the state of the program. So it becomes a program synthesis problem, and the program synthesis problem is synthesizing a program that has the following form. It's a bunch of if-else statements that say if something is true, use this coupling, otherwise use that coupling. So, if you really want to see a proof of the report noisy max example, I can show it to you, and it looks something like this. So we've applied this to a number of different programs from the literature, and we managed to prove them correct in a matter of a minute or less than a minute sometimes. Okay? So both the accuracy proofs as well as the differential privacy proofs. Okay? Now, of course, this does not solve the verification problem for differential privacy. There are so many extensions of differential privacy. There are so many algorithms that are just inherently hard for verification. Like some algorithms, construct a linear program and then call a linear program solver. And then at that point, I don't know how to, use an SMT solver to encode an LP solver. And, it's really tricky. Okay. So that's the story. So accuracy, privacy, really hard things. Turns out that we can use SMT solvers. That's all. Thanks.
Hey, thank you. Questions? Yeah.
Great talk.
Thanks.
Thank you. So I'm wondering, you're using this to prove a statement about a single program under a condition on a region of inputs, right? Mm-hmm. Or two similar inputs.
Right.
Do you think this coupling argument could be applied to two different programs? So if I want to show that two probabilistic programs, generally speaking, have a similar distribution. Yeah. Is it still the coupling? How dependent is this on having you're analyzing one program
Yeah, so that's a good question. So the question is, you have two different programs that are completely syntactically different. Can you apply the same argument? In principle, yes, but a lot of the proofs of hyperproperties, meaning properties that involve two different programs, have a lot to do with syntactic structure. So even if you're not looking at probabilities, just something like associativity or commutativity or just program equivalence, there's a lot of syntactic structure that has to be taken into account. So in our case, for instance, we have to assume that the loops are synchronized. Okay? So you're running two programs, they execute the same number of loop iterations and things like that. In principle, you have another search space where how do you take two syntactic structures, two graphs, and how do you align them? And that is another piece of the search. If you can do it, then you can apply this. Yeah.
Thank you. Any other questions? Yeah.
So also, for the closed form, right? You look at a couple of distributions. For other distributions, can you always get a closed form?
Most well-behaved distributions like Laplace, exponential, Gaussian, you can characterize the area under the curve in such a form. Yeah.
Okay, I see. Suppose that the post condition somehow is too strong.
Yeah.
Right. If your proof fails, what will happen? Yeah.
That's a good question. So what happens if the proof fails? The proof system is incomplete and it does not produce counterexamples. So I don't have a story for counterexamples or refinement or anything like that. But you could imagine an inverse proof system that's trying to, in a sense, our proof does an under approximation to get a bound on some probability. You could imagine another proof system that is doing an over approximation to get another bound. And if one of them fails, then you switch to the other. But I don't have a good story for that. Yeah.
Okay, let's take a last question from Alex. Oh, sorry. Well, Alex had a question, and maybe another last question from Martin afterwards.
So yeah, thanks for a great talk.
Yeah,
it's
thanks.
Extremely intriguing work. I'll probably chat to you in the coffee break too. I'm a bit puzzled about the multiplication for loops. So in the first part of the talk, it seems you multiply this essentially constant quantity that says what's the probability of failure per loop iteration. So now I have the feeling in the second part, it's still it's more refined, right? But it's still basically not loop dependent, right? Your expression for how much did it go wrong per loop iteration is still, I assume, something that gets multiplied in the end by a constant.
Yeah, so in the case of report noisy max, you were getting p divided by the number of loop iterations. And then since you execute the loop q times, then you end up paying p at the very end.
Yeah, so I guess what puzzles me is, on the one hand, can it not be that the right amount per loop iteration is just different every time?
It could be.
The other aspect is, how do you know what to multiply by? How do you know how many loop iterations?
Oh, how do you know how many loop iterations? Is because the inductive invariant comes in, and that gives you a bound, and then that implies the final probability of failure. Yeah. So that's the part I left out, which is the loop invariant. Yeah.
Okay. Thanks.
Yep, nice work. So I had a question, a couple of questions. So the first one was on, this kind of work reminds us when you're estimating, essentially you're getting part of the density of the distribution, right? This is this, and then the rest is the error. So this kind of reminds of this paper that I think Alex Chakarov had with Sumit and Theorem in PODI, where they had one part was exact, and then the rest was bounded by some range.
It has a similar feeling. Yeah. There are two differences. Both have to do with the symbolic nature of this proof. So in their case, they had a program that is essentially a generative model. You just execute it. It does not have any inputs. And there are no parameters in the distributions. So the distribution is there. You can just estimate it. In our case, we have a universal quantifier at the outside. So for every database, you have to do that, which is impossible. Yeah.
And then one last quick question. So this thing, with the accuracy and robustness, the property, here, differential privacy. So there is a lot of work in this in machine learning, this trade-off. Did you look at it in this context, not just proof for accuracy or proof for differential privacy, but studying the there is a trade-off between these two usually.
Yeah, there is a trade-off. We have not studied it. So, I mean, the accuracy proofs are kind of funny because in practice, I mean, the accuracy theorems that you have do not indicate that the algorithm works well for real-world workloads. So it just kind of gives the algorithm designer a sanity check that they're not egregiously returning bad results. But we have not looked at that trade-off. It'd be interesting. Yeah.
Okay, so thanks again.
Yeah, thank you.